Welcome back. So now we're going to talk about the very last thing that you need to know in order to build Pac-Man, and that's known as hill climbing. So exactly what hill climbing is. It's just a technique that's used very often to find the optimal value of some function. So this is a crazy example, but think of economics. And economists always talk about a utility function that describes how good something is in terms of some various input variables, like, for example, how good life is if you spend half your money on vacations. Okay, so what you'd like to do is optimize that. So you want to optimize the goodness of life based on how much money you spend on vacations versus other necessities. And well, honestly, that's a lot of the mathematics of economics. So what we'd like to do is to solve these problems in general by trying this. We don't know how much money to spend on vacation, so let's just start with, say, 100%. Okay, that sounds pretty reasonable. Um, but we may discover that that's actually an untenable position, and that means that we need to change what we have, and you change in the direction in which the goodness is most likely to increase. Okay, so basically, think of the goodness as being some sort of a hill, and you find the steepest route up the hill, and you climb in the steepest direction. Okay, so that's the notion of hill climbing. It's just, where are we? Are we at the top? No, we're not. Okay, in what direction does the top look like it is based on what's steepest from here? Let's go that way, and eventually you walk your way up to the top of the hill. Now, technically, hill climbing is slightly different than what I just described, because in hill climbing, you can only go, for example, due east, due west, due south, due north. That's it. Okay. So in general, you can only go down certain axes, and and those are your only options, right? If you actually look in the terms of steepest, what you're doing is something called gradient descent, which is more general. Now, for our purposes, it's not really important, so we'll just call it hill climbing, um, and continue along with that. Okay. Now, in many cases, when the function is really, really nice, like, for example, if it's convex, then hill climbing will work. Okay, it's completely guaranteed to find the answer. If the function isn't very nice, and the easiest example of a not nice function is when it has multiple peaks, then hill climbing is not guaranteed to work. You may, for example, find yourself at a local maximum, so you're at the peak of some hill. The problem is that there's a hill next door that's a lot better, and so you don't actually get the best possible solution, but you get a nice solution nevertheless. Both diffusion and hill climbing have a really, really long history in gaming. Okay, and this is actually best seen by the original Pac-Man, which was both algorithms to great effect. So the diffusion idea we've talked about, and that is that Pac-Man has a presence or a smell. Different books call it different things, and as Pac-Man moves around, it leaves that smell in its location. Okay, um, then that dissipates. So it's very strong close to where Pac-Man is, and is a little strong where Pac-Man was not too long ago, and it's pretty weak where Pac-Man was quite a while back. Now, what the ghosts are doing is they're basically sniffing for Pac-Man, and once they get some sort of a scent, okay, then they start climbing the hill. And what does that mean? It means that they look around and go, okay, in which direction is the scent getting stronger? That way. That's where they move. That's the extent of the intelligence of the ghosts in Pac-Man, and that's all it takes, really. Okay. Now, just to be clear, they don't just do that. Okay. At the very, very, very end, which is, say, when they're within three um, cells of Pac-Man, then they switch into a slightly more complicated setup, which is that they consider all of the possibilities. And so they do like a little plan, and that's the reason that they can sometimes trap Pac-Man, so that there's absolutely no way for it to be able to go. In fact, it looks like they're cooperating, even though they're really not. But the bulk of the algorithm is actually done strictly with presence. And if all you do is this hill climbing and diffusion, you can get a very, very realistic game of Pac-Man, and that's the game that we'll be building. Now, I'm going to show you a demo of that in the next video. But for now, I just want to say that hill climbing is really useful in a lot of other contexts, not just in Pac-Man. Remember, this is an optimization technique, and there's lots of problems that look like they require some optimization. So here are some examples. This is from economics. I need to make some bagels. That means it costs me some materials. On the other hand, I sell them for a certain profit. How many bagels should I make each morning to maximize the profit? Okay, this is something that a lot of students deal with. How many hours should I spend working as opposed to studying to maximize my future earnings? And sometimes it's a very stark choice, like should I go back to school? Well, that's an optimization problem. Okay. Here's a related problem. Let's say that I'm doing urban planning and I'd like to place 3, for example, fire stations in a city. I want to minimize the response time, so where should they be? Okay. Lots of problems in science, for example, the arrangement of molecules. Some of these problems are really difficult, like protein folding. But depending on the arrangement that you have, you generate some sort of potential energy. I'm saying gravity in this example, but honestly, in chemistry, you can ignore that completely. What you can't ignore is the intermolecular forces. So you want to minimize those. And again, that's an optimization problem. It's a pretty hard one. Okay. How do you know whether a student is going to be successful in college? So you might look at lots of different criteria, like their GPA in high school, standardized test scores, recommendation letters, all sorts of things. And then we have to make a decision. This student is likely to succeed. Again, that's an optimization problem where you're trying to optimize, for example, the pool of students that you accept to an exclusive university. So there's actually a lot of different tools that are applied to this. We talked about hill climbing, which is a pretty general technique, but there are some others, like for example regression, where we're minimizing some sort of error. That can be used to a lot of these problems. For example, you can build a regression model that helps to explain the likely success of a student based on all those different factors. And this is kind of in a more general sense what we call data mining, which is of course the buzzword of the day. And data mining is huge. It has a lot of mathematics in it, like for example statistics. It has a lot of other tools from computer science. And some of the stuff that we're doing in these games, like hill climbing, actually fits that space fairly nicely. So it's, if nothing else, is a good thing to be able to tell people about the connections with what we're learning. Anyway, let's get to the actual details of hill climbing, and for that I'll show you the code in the next video. I'll see you there.